In the previous two lectures, we have discussed the Hahn-Banach theorem, one of the most fundamental results in the whole functional analysis. And there are two more, not less fundamental results than the Hahn-Banach theorem. They are the open mapping and the closed graph theorem. But before we discuss the closed mapping and the open mapping and the closed graph theorem, we need to discuss the notion of an inverse operator. So we have already discussed the linear operators, and we know that the set of all linear operators from one linear space to the other linear space can be equipped with algebraic operations. So we can add up two operators and we can multiply operators by scalars. So the reasonable question is, can we do some more algebraic operations with linear operators? For instance, can we multiply two operators? So the topic for today is invertible operators, but let us first discuss the multiplication. So throughout the lecture, let us fix x and y to be linear spaces, non-linear spaces. So we know that the space of bounded linear operators from x to y is a normed linear space as well. So the question is, can we multiply two operators? You can easily figure out that the matrices are the linear operators between finite dimensional linear spaces. Even on the level of the matrices, the answer for this question is not certainly yes. Because to multiply two matrices, we have to match their sizes, or rather the dimension of domains and ranges. So the similar thing applies here for the case of general linear operators. So let us start with a definition. So let us consider three normed linear spaces, and let us consider two operators A be a bounded linear operator from y to z, and B be a bounded linear operator from x to y. Then we can define a composition of these two operators. So A composed with B, acting on an element x from the space x, which is by definition is A applied to B of x. Which is well defined for any element from x, because B acts from x to y, so B of x is an element of y. And so we can apply we can apply an operator A to this element, which maps that element y into z. So this composition is well defined, and it is called a product of two operators A and B. In this case, we denote it by AB. So okay, under certain conditions on the domain and codomain of operators, we can multiply two operators. Let me state a fairly straightforward properties of the product of operators. So let us suppose that the product of A and B exists. The norm of AB is less than or equal to than the product of norms, which is fairly straightforward from the definition of the norm of an operator. As we have just discussed, for the product to be well defined, we need some kind of agreement between the domains and codomains of these two operators. This can be easily avoided if we consider the operators on the same space. So, yeah, that will be one, and this will be the second point. If A and B are bounded linear operators on the same space, then their product defined moreover, AB, both AB and BA are defined. But, as you might remember from the algebra, these two operators are not necessarily equal to each other. Or in other words, the product of operators is not necessarily commutative. We have discussed how to define the product of two operators. Well, after we have defined the product, what about the division of two operators? Again, from the reality of matrices, we did not use the term the division. We did not divide one matrix by another, but we rather use the notion of the inverse matrix. And again, from the reality of matrices, you remember that not every matrix is invertible. Well, the same will be the case for bounded linear operators, so not every operator is invertible. But let's first of all define the notion of invertible operator and then discuss the conditions for an operator to be invertible. We denote by I sub x and I sub y the identity operators. Respectively. And let us take an operator A from x to y. An operator bounded linear operator from x to y is called invertible. If there exists an operator B from y to x such that A times B is identity and B times A is identity. And this one is identity in Y and this one is identity in X. In this case, the operator B is called the inverse of A. And we denote A inverse. Let me state the simplest properties of the invertible operators and the inverses. So let x, y, and z be non-linear spaces. A be a bounded linear operator from y to z, and B be a bounded linear operator from x to y. And we suppose that both of these operators, A and B, are invertible. The inverse operator is unique. Well, the inverse of B is unique as well, but that will be the same statement. Moreover, the inverse operator, A inverse, is invertible, and well, its inverse is A. Well, since we've chosen the domains and codomains of A and B in this specific way, the product AB exists, and moreover, it is an invertible operator. Is invertible with inverse, B inverse, A inverse. Moreover, we have some inequalities between the norms of the operator and its inverse. For any x from x, we have that the norm of ax is less than or equal to the norm of A times the norm of x, which is not surprising by the definition of the norm. The new one is the estimate from below, which is the norm of x over the norm of A inverse. All these properties are fairly simple, so I'll leave it for you as an exercise to prove. Let us consider an example. The example will be the multiplication operator. So let us fix a continuous function on the interval 0, 1. And consider an operator M sub f from this space to itself. And let me note that we equip this space of continuous functions with the uniform norm. Oh, well, nice. Yeah, I said that we consider the multiplication operator, stated the domain and the codomain. The formula is missing, given by. So mf acting on a function u equals to f of t times u of t for any continuous function u from 0, 1, defined on 0, 1. So, well, it is in fact a multiplication operator. It is linear. It's fairly easy to see. Let us prove that it is bounded, which is also very difficult to see. So we have the norm of mf at the point u equals to the maximum of mf of u at the point t. Now I will use the definition. Now we can split the absolute value of a product and take the maximum of each term. Still over the interval 0, 1. Which is nothing but norm f times norm y. This tells us that the operator is bounded and its norm is less than or equal to the norm of f. Let me write down the norms. Everywhere over here we have the infinity norm, and this norm is the operator norm. If we take the function u to be constantly 1, then we will show that the norm of mfu equals to just the norm f. And let us consider a specific example of multiplication operator where we choose a particular function f. Let us take f to be 1 plus t. So having chosen this function f, it's not difficult to directly construct an inverse operator for the operator mf. So I say that mf, the operator, is invertible and its inverse is also a multiplication operator. So it's a multiplication operator by the other function g, where this g is 1 over f. Which is defined and is a continuous function. Note that g is an element of the space. Let us briefly check that mg is in fact the inverse. Mg times mf at some function u at u at the point t equals to g of t f of t times u of t, which is nothing but u of t, because g is inverse of f as a function, which tells us that mg mf is the identity. Similarly, we can show that mf times mg is identity as well, and therefore m sub g is the inverse of mf. Yeah, so first of all, mf is invertible and its inverse is mg. Well, we have considered a multiplication operator for a specifically chosen function f, and without any problems proved that it is invertible and computed its inverse. As you might guess, in the general situation, the life is not as easy as here. Let's consider one more example. So let us consider another multiplication operator. M sub h, still on the same space, with the function h being equal to t. In the previous example, to construct the inverse of the multiplication operator, we've taken the inverse of the function. And that inverse was well defined on the interval 0, 1 and was a continuous function. This is not the case here, so the inverse of h is not even defined on the interval 0, 1. So we cannot construct the inverse in the way we did it before. But this doesn't let us to conclude that the operator mh is not invertible, and moreover, we cannot even conclude that if mh is invertible, then its inverse is not a multiplication operator. Although, yeah, it is not invertible. So let me write this down. Well, neither we can conclude that it is invertible, of course. Even in this example, where we made the situation is a little bit more complicated, we cannot easily compute the inverse, nor we cannot even decide whether the operator is invertible or not. So dealing with the general situation, we need more results, we need more magic to treat it. So let me state a theorem which tells us the condition under which the operator is invertible. In this result, we restrict our attention to operators acting on the same Banach space. And let us consider on this Banach space X a bounded linear operator such that its norm is strictly less than 1. Having these assumptions, we conclude that the operator identity minus A is invertible, and moreover, we have a very nice formula for its inverse. Its inverse equals to an infinite sum of powers of A. Formula can remind you of some formula from calculus. So these can be compared with the formula 1 over 1 minus x equals to the series of from 0 equals to this series. This formula holds for any x with the absolute value strictly less than 1. So let us first use the condition that the norm of operator A is strictly less than 1. Then, let us consider the numerical series This numerical series is nothing but the power series, with the base of that power being strictly less than 1, so it converges. Further, as soon as we introduced the product of two operators, I stated a very simple inequality between the norm of the product and the product of the norms. So let's use it over here. But this inequality tells us that the other series is convergent. But this kind of condition tells us that the operated series converges. Moreover, it converges in norm or uniformly. Well, this series converges. Let me denote, well, converges to some element of the space, so to an operator. So let me define this operator by S. And let me denote by S sub k the partial sums of this series. Okay, let me just mention that we have just proved that this sequence Sk converges to S uniformly from 0. Yeah, correct. I was right up to here, here, and here. It is 0 and 0. Yeah, if we start at 1, it will not work. And we are about to see this. So let us consider the following expression. Well, again, the idea behind it, so what I want to do, I want to show that this operator S is the inverse of identity minus A. So what I'm doing here, I multiply identity minus A by the partial sums of that inverse, or rather inverse to be proven. And I want to show that it is close to identity. So what we have here is identity minus A to the power of n, all. Let me write down the k plus 1 terms of this sum. So a to the power of 0 is by definition identity plus a squared plus up to a to the power of k minus identity. If we multiply this now, we will get identity plus a plus up to a to the power of k minus a plus a squared plus up to a k to the power of 1, a to the power of k plus 1 minus identity. Almost all of the terms cancel each other out except this one, a to the power of k plus 1. This expression is just the k plus first term of the series which converges, which means that as k tends to infinity, these terms tend to 0. That is, the limit of this operator equals to this operator. Further, we have identity minus A times S equals to identity minus A times the limit of Sk by definition of S and the definition of Sk. And then we will use the linearity of limit and of operators to write it down as the limit which is identity, as we have just proved. In a similar fashion, it can be shown that S times identity minus A also equals to the identity, which means that identity minus A is invertible and its inverse equals to S equals to the series. And we're done. Thank you for correcting me. Yes, 0 everywhere. This fairly simple result has a very nice corollary, which will be an exercise for you to prove. If we consider the set of all invertible bounded linear operators on some space, then this set is open. Let me state and prove one more simple but useful result about the invertibility of operators. So let X be a Banach space, and let us consider a bounded linear operator on X which is invertible. If we consider a second bounded linear operator on X which is in some sense close to A, and it is close to A in a sense that the norm of A minus the norm of B is strictly less than 1 over the norm of A inverse. Then we can conclude that B is invertible. So first of all, let us write B as follows: A times identity minus A inverse times A minus B. Yep, over here we have identity minus A and identity cancel each other out. And over here we will have A inverse B, and over here it's A, so it's B in fact. And now let us use this estimate on the norm of A minus B to prove that, to conclude the norm of A inverse times A minus B is less than or equal to the norm of A inverse times the norm of A minus B, which is strictly less than 1 by our assumption. Hence, by the previous result, the operator which we have inside over here is invertible. But we have written B as a product of A and this operator. And we know that A is invertible and this operator is invertible. So B is invertible as well. And its inverse equals to I have one more exercise for you. Let us consider the differentiation operator. And the exercise for you will be to check whether this differentiation operator is invertible. And if it is, then what's its inverse? I have intentionally not defined this differentiation operator in full, because, well, to define an operator or any mapping, we need to specify not just formula, but the domain and codomain. So that I have intentionally did not specify that to make this problem more substantial for you. As you remember, this differentiation operator is not even bounded if considered from the space of continuously differentiable functions to continuous functions if we just equate both of these spaces with the uniform norm. So this exercise again is rather more substantial for you to figure out where it should define in which spaces it is bounded, and then only after that we can speak about the inverses. Let us now very briefly discuss how the properties of an operator being isometry or isomorphism are translated to its inverse. And well, as a spoiler, they are transferred very nicely. So let me just state this proposition. It's the proof of this proposition is well, pretty much straightforward. So let x and y be two normed linear spaces. First, if A from x to y is an isomorphism, then its inverse, its inverse is an isomorphism as well. First of all, I have not even specified that A is invertible, because when we have an isomorphism, it is a one-to-one, and it is surjective, so it is onto. So the inverse mapping is defined simply because it is an isomorphism. So we just need to claim that it is an isomorphism too. And the second property, if an operator is an isometric isomorphism, then its inverse possess exactly the same property. So it is also an isometric isomorphism. I will finish this lecture with an example of shift operators on the space of sequences. Let L2 be the space of square summable sequences. And let us consider the left and the right shift operators on this space. Two operators, S and T, from L2 to L2, given by S of x1, x2, and so on, equals to 0, x1, x2, and so on. So the first operator is a shift to the right, so it's a right shift. It adds 0. And the second operator, T, is the left shift. So it shifts the sequence to the left, removing one element. So first of all, it is easy to see that both of these operators are linear. Let us quickly check that they are bounded. The norm of S of x, the two norm we are in L2, is the sum of all coordinates of Sx I squared, the square root. So the first coordinate of S is 0, but all the rest of the coordinates are the coordinates of X, and it contains all of them. So what we have is nothing but the sum over all X's. The norm of X in L2. Also, it is not difficult to see that the operator T is bounded as well. But over here we are missing the coordinate x1. But we can estimate it from above by the whole sum starting from 1, which is the norm of x. So T is bounded and the norm of T less than or equal to 1. To compute the exact value of the norm of T is left for you as an exercise. Let us consider one more interesting property of the operator S. The operator S, in fact, consider, we have already proved that. We already proved over there that the operator S is isometry. It is easy to see that T is not an isometry. And I was about to prove this, but then I figured out that by doing so I will compute the norm of T for you, so I will not do this. So T is not an isometry, and computing the norm of T you will figure this out. Showing that S is isometry, however, on the other hand, T is not an isometry. However, T is a surjective operator, so it's onto, whereas S is clearly not onto. Because, the range of S consists of all sequences from L2 with 0 at the first coordinate, which is definitely not the whole L2.